Hey everyone, welcome to PLA Academy. Hope you found this video useful. If you did, it'd be awesome if you could subscribe, like the video, share it with your friends, and maybe drop a comment. Your support really helps me make more videos. In this video, I covered everything on the syllabus, like you can see in the figure. Electric current. The electric current is the amount of charge passing a point per second, or the rate of flow of electric charge past a point. We can write the formula of electric current as Q equals IT, where Q is the amount of charge in coulomb, I is the electric current in ampere, and T is the time in second. 1 coulomb is equivalent to 1 ampere second. This means that 1 coulomb is the charge which flows past a point in a circuit in a time of 1 second when the current is 1 ampere. The charge has two types as positive and negative charges. The direction of current is the same as the direction of movement of positive charges, but opposite to the direction of movement of negative charges. Charge carrier. The current is the flow of charged particles called charge carriers. Electrons each carry a tiny negative charge of approximately negative 1.6 times 10 power negative 19 coulombs. This charge is represented by negative E. The magnitude of the charge is known as the elementary charge. Protons are positively charged, with a charge positive E. This is equal and opposite to that of an electron. Ions carry charges that are integer multiples of positive E and negative E. The electric charge is carried by particles. It must come in amounts, which are integer multiples of E. For example, 3.2 times 10 power negative 19 coulombs is possible, because this is positive 2E. While 2.5 times 10 power negative 19 coulombs is impossible, because this is not an integer multiple of E. Therefore, the charge on charge carries is quantized. This means that the charge carries can only have in amounts of charge, which are integer multiples of 1.6 times 10 power negative 19 coulombs. A current-carrying conductor. A current I in a conductor wire of cross-sectional area A. The charge carriers are free-moving electrons with mean drift velocity v. The conductor wire has the n free-moving electrons per unit volume, and each electron carries the charge of E, which is 1.6 times 10 power negative 19 coulombs. We can write the formula of the electric current I as I equals NAVQ, where I is the electric current in ampere, N is the number of charge carriers per unit volume in per cubic meters, A is the cross-section area in cubic meters, V is the drift velocity of charge carriers in meters per second, and Q is the elementary charge E, which is 1.6 times 10 power of negative 19 coulombs. The number of charge per unit volume N is sometimes called the charge carrier's density N, which is a material-specific property, meaning that all samples of the same material have the same charge carrier's density. We can derive the formula I equals NAVQ as follows. In the time t, all of the electrons in the length L of wire are moving through the wire with the cross-section area A. This creates the electric current I in the opposite direction as the electrons moved. The conductor wire contains the number of charge carriers, or electrons, per unit volume N. This is called charge carriers density. The volume of the conductor wire equals the cross-section area A times the length L. The total number of electrons in the length L of the conductor wire equals N times AL. Each electron carry the charge Q, which is the elementary charge, E equals 1.6 times 10 power of negative 19 coulombs. So, the total charge Q in the length L of the conductor wire equals Q times N times AL. Therefore, the electric current I flows through the wire equals total charge Q divided by time t, where the length L is divided by t equals the drift velocity v of charge carriers, which is electrons. So, the electric current I equals Q NAV. Exam style question 1. Free electrons flow along a copper wire X of radius 5.0 times 10 power of negative 5 meters, with an average drift speed of 2.8 times 10 power of negative 2 meters per second. The current in the wire X is 3.0 amperes. There is a current of 2.0 amperes in a copper wire Y of radius 1.0 times 10 power of negative 4 meters. What is the average drift speed of the free electrons in copper wire Y? The wires X and Y are made of the same material, copper. The number of free electrons per unit volume, N, is the same for both. We calculate the N first using the equation I equals NAVQ, rearranging the equation as N equals I divided by AVQ. Substituting I equals 3 amperes, cross-section area A equals pi squared of 5 times 10 power of negative 5, drift velocity V equals 2.8 times 10 power negative 4, and Q equals 1.6 times 10 power negative 19 coulombs. We get the N equals 8.526 times 10 power 28 per cubic meters. We calculate the drift velocity in a wire Y using V equals I divided by NAQ. Substituting I equals 2 amperes, N equals 8.52 times 10 power 28, A equals pi squared of 1.0 times 10 power negative 4, and Q equals 1.6 times 10 power negative 19 coulombs. We get the V equals 4.7 times 10 power negative 3 meters per second for two significant figures. Exam style question 2. 4-point charges, each of charge Q, are placed on the edge of an insulating disk of radius r. The disk rotates at a rate of n revolutions per unit time. What is the equivalent electric current at the edge of the disk? 4-point charge Q on the disk rotate n revolution per unit time. This causes the total charge passing a point per unit time to be 4qn. Since the charge passing a point per unit time is 4qn, therefore, the electric current at the edge of the disk is 4qn. Exam style question 3. Two copper wires are joined together and carry a current, as shown. Wire P has diameter d, and wire Q has diameter 2d. What is the ratio average drift speed of the free electrons in wire P to average drift speed of the free electrons in wire Q? From the equation I equals NAVQ, rearranging the equation V equals I divided by NAQ. The wires P and Q are made of the same material, copper. The number of free electrons per unit volume, N, is the same for both. Both wires are connected in series. The current flows through both wires is the same. Q is the constant value of 1.6 times 10 power negative 19. The cross-section area A equals pi diameter d squared and divided by 4. So, the drift velocity in wire P equals I divided by nq pi d squared over 4 and simplified like this. The drift velocity in wire Q equals I divided by nq pi 2d squared over 4 and simplified like this. We divide Vp by Vq, and simplifying the equation like this. And cancelling I, n, q, pi and d squared, like this. We get the ratio Vp to Vq equals 4. Exam style question 4. A metal plate of uniform thickness is connected to a cell as shown. Electrons move clockwise around the circuit. Which statement about the metal plate is correct? From the equation I equals NAVQ. The current I is constant through metal plate. The number of free electrons per unit volume N is constant through metal plate. The elementary charge Q is constant value as 1.6 times 10 power negative 19. The cross-section area A decreases from right to left. So, V is inversely proportional to A. This causes the average drift speed of electrons increases from right to left. Choice A. The average drift speed of the conduction electrons decreases as they move from right to left through the plate. This is incorrect. Choice B. The average drift speed of the conduction electrons increases as they move from right to left through the plate. This is correct. Choice C. The number density of the conduction electrons decreases from right to left through the plate. This is incorrect. Choice D. The number density of the conduction electrons increases from right to left through the plate. This is incorrect. Hey everyone, welcome to PLA Academy. Hope you found this video useful. If you did, it'd be awesome if you could subscribe, like the video, share it with your friends, and maybe drop a comment. Your support really helps me make more videos. In this video, I covered everything on the syllabus, like you can see in the figure. Potential difference, or PD. The potential difference is called sometimes voltage. The potential difference is the work done, or the electrical energy transferred, to other forms of energy per unit charge, that passing charge through a component. We can write the formula of potential difference as V equals W divided by Q, where V is the potential difference or voltage in volt, W is the energy transferred, or work done in joule, and Q is the charge in coulombs. 1 volt is equivalent to 1 joule per coulomb. The circuit diagram is shown. The voltmeter readings across each resistor and power supply indicate the energy transferred to the component by each unit of charge. The voltmeter placed across the power supply measures the EMF of the supply as 12 volts, indicating that the battery provides 12 joule of electrical energy to each coulomb of charge that flows through the circuit. The voltmeter placed across the 20 ohm resistor measures the potential difference, PD, as 8 volts, meaning that 8 joule of electrical energy are converted to heat energy for every coulomb of charge passing through the resistor. The voltmeter placed across the 10 ohms resistor measures the potential difference, PD, as 4 volts, meaning that 4 joule of electrical energy are converted to heat energy for every coulomb of charge passing through the resistor. The current flows from higher voltage to lower voltage. The circuit diagram is shown. The EMF of the power supply is 12 volts, indicating the PD across the supply is also 12 volts. We know that the current flows from the positive to negative terminal. So, the voltage at point A equals 12 volts, and the voltage at point F equals 0. This causes the PD across AF equals 12 volts. We assume that the wire has no resistance, so no energy loss and no PD loss along the wire. The voltage at any point along the pink wire is 12 volt, and the voltage at any point along the green wire is 0 volt. So, the voltage at point A, B and E equals 12 volts. This causes the PD across AB and BE equals 0. The voltage at point F, D and H equals 0. This causes the PD across DF and DH equals 0. The PD across BC equals 8 volts, and voltage at point B equals 12 volts, so voltage at point C equals 4 volts. The PD across CD equals voltage at point C minus voltage at point D, which is 4 minus 0 is equal to 4 volts. The PD across EG equals 3 volts, and voltage at point E equals 12 volts, so voltage at point G equals 9 volts. The PD across GH equals voltage at point G minus voltage at point H, which is 9 minus 0 is equal to 9 volts. The PD across GC equals voltage at point G minus voltage at point C, which is 9 minus 4 is equal to 5 volts. Electrical power. The electrical power, P, is the work done W, or energy transfer E, per unit time t. We can write the equation as P equals W divided by T, where P is the electrical power in watts, W is the work done, or energy transferred in joule, and T is the time in seconds. 1 watt is equivalent to 1 joule per second. The electrical power, P, of an appliance, or components, is related to its resistance, R, the voltage V, across it, and the current, I, flowing through it. We can write the equation as P equals VI or equal I squared, R or equal V squared over R, where V is voltage in volt, I is the current in ampere, and R is the resistance in ohm. We can derive the formula of P equals VI as follows. From the formula V equals W over Q, and rearranging the equation as W equals VQ. Substituting W equals VQ into P equals W over T, like this. And I equals Q over T. So, P equals VI. We can derive the formula of P equals I squared R as follows. From the formula P equals VI, and V equals RI. Substituting V equals RI into P equals VI, like this. So, P equals I squared R. We can derive the formula of P equals V squared over R as follows. From the formula V equals RI, and rearranging the equation as I equals V over R. Substituting I equals V over R into P equals VI, like this. So, P equals V squared over R. Electrical energy, we can write the formula as E equals VIT. We can derive this equation as follows. From the equation P equals energy transferred E over T, and rearranging the equation as E equals PT. Substituting P equals VI into this equation, like this. So, we get the equation E equals VIT. 2 resistors, 20 ohms and 10 ohms, are connected in series to a 12-volt power supply, as shown. Which resistor will dissipate the highest power? Resistors X and Y are connected in series, meaning the same current flows through both. According to the power equation P equals I squared R, power is directly proportional to resistance when current is constant. Therefore, the resistor with the highest resistance will dissipate the highest power. In this case, resistor X, with a resistance of 20 ohms, will dissipate the highest power. 2 resistors, 20 ohms and 10 ohms, are connected in parallel to a 12-volt power supply, as shown. Which resistor will dissipate the highest power? Resistors X and Y are connected in parallel, meaning the same potential difference, PD, is across both. According to the power equation P equals V squared over R, power is inversely proportional to resistance when voltage is constant. Therefore, the resistor with the lowest resistance will dissipate the highest power. In this case, resistor Y, with a resistance of 10 ohms, will dissipate the highest power. Exam-style question 1. A conductor consists of 3 wires connected in series. The wires are all made of the same metal, but have different cross-sectional areas. There is a current I in the conductor. Point Y on the conductor is at zero potential. Which graph best shows the variation of potential V with distance along the conductor? From the equation V equals RI. The current I flows through the conductor to be constant. So, the PdV across the conductor is directly proportional to the resistance. Recall that the resistance, R, is directly proportional to the length and inversely proportional to the cross-section area. So, the first section of the conductor has the resistance R1 and the PD across it is V1. This section has the largest cross area A, resulting in the lowest resistance. This causes the PD across R1 to be smallest. As the conductor's length, L, increases, the PD across conductor continuously decreases. So, the choice C and D are incorrect. And the PD V1 across R1 for choice A and B like this. The second section of the conductor has the resistance R2 and the PD across it is V2. The resistance R2 is more than R1 due to the cross-section area A2 less than A1, so the PD V2 is less than the PD V1. The PD V2 for choice A and B like this. So, A is correct. The third section of the conductor has the resistance R3 and the PD across it is V3. The resistance R3 is more than R2 and more than R1 due to the cross-section area A3 less than A2. So the PD V3 is less than the PD V2 and less than V1. Exam style question 2. 3 resistors are connected in parallel across a power supply, as shown. The power dissipated in each of the resistors of resistance 2 ohms, 3 ohms and 4 ohms is P2, P3 and P4, respectively. What is the ratio P2 to P3 to P4? From the equation P equals V squared over R. The voltage V across each resistor is the same as the EMF of the power supply, because the resistors are connected in parallel. So, the power dissipated at each resistor is inversely proportional to its resistance. This gives us the ratio P2 to P3 to P4 equals 1 over 2 to 1 over 3 to 1 over 4. We simplify the ratio by multiplying each term by 12, like this. We get the ratio as 6 to 4 to 3. Exam style question 3. In the circuit shown, a fixed resistor X is connected in series with a battery and a variable resistor. The power dissipated in resistor X is 7.2 watts when a current of 3.0 amperes passes through it. The variable resistor is adjusted so that the power dissipated in X increases by 50%. What is the new current in the circuit? From the equation P equals I squared R. Substituting P equals 7.2 watts and I equals 3 amperes. We get the resistance Rx equals 0.8 ohms. As the power dissipated Px increases 50%, which is 1.5 times 7.2 watts equals 10.8 watts. Substituting Px equals 10.8 watts, Rx equals 0.8 ohms. We get the new current equals 3.7 amperes for 2 significant figures. Hey everyone, welcome to PLA Academy. Hope you found this video useful. If you did, it'd be awesome if you could subscribe, like the video, share it with your friends, and maybe drop a comment. Your support really helps me make more videos. In this video, I covered everything on the syllabus, like you can see in the figure. Resistance is the ratio of potential difference V across a component to current I in a component. We can write the formula of the resistance as R equals V divided by I, where R is the resistance in ohm, V is the PD, or voltage across the component in volts, and I is the current in ampere. 1 ohm is equivalent to 1 volt per ampere. 4 factors affect the resistance of a metallic conductor wire. 1. Temperature. As temperature increases, the resistance of a metallic conductor increases. This is because the atoms in a conductor gain the kinetic energy and vibrate more, which reduces the rate of flow of charges. This causes the current to decrease, the resistance increases. 2. Type of material. Different materials have different resistance. This is because the number of charge carriers per unit volume N is different for different materials. Greatest N, lowest resistance. 3. Length of a conductor wire. Resistance, R, of a wire is directly proportional to its length of L. The longer a wire, the greater its resistance, and vice versa. This is because electrons collide with more ion atoms, and decreasing the rate of flow of charges, and so there will be more resistance. 4. Cross-section area of a conductor wire. Resistance, R, of a wire is inversely proportional to cross-sectional area, A. The thicker a wire, the smaller its resistance and vice versa. This is because there is more space for electrons, and so more electrons can flow. The cross-section area A of a wire is a circular, which is pi radius r squared, or pi diameter d squared over 4. So, the resistance will inversely proportional to radius r squared and also inversely proportional to diameter d squared. Therefore, we can deduce that the resistance is directly proportional to length L and inversely proportional to the cross-section area A. We can write the equation of the resistance as R equals ρ L over A, where ρ is the resistivity of each material in ohmmeter, L is the length in meters, and A is the cross-section area in square meters. The resistivity ρ is a material-specific property, meaning that all samples of the same material have the same resistivity. IV characteristic graph of a metallic conductor at constant temperature. The graph of current I in amperes against voltage V in volts is shown. The graph of voltage V in volts against current I in amperes is shown. Both graphs are the straight line and passing through the origin. These show that the current is directly proportional to the voltage across a conductor. The gradient of graph is constant, so the resistance of the conductor remains constant as temperature also constant. When a battery reversed, causing the current to flow in opposite direction. On the both graphs, these sections shown the battery to reverse. In this graph, its gradient equals current divided by voltage, which is 1 over the resistance. In this graph, its gradient equals voltage divided by current, which is the resistance. IV characteristic graph of a filament lamp. The graph of current I in amperes against voltage V in volts is shown. The graph of voltage V in volts against current I in amperes is shown. The graph is not a straight line, indicating that the resistance of the bulb changes. In these sections of both graphs, the battery is reversed, causing the current to flow in opposite direction. The gradient of both graphs are changed. This shows that the rate of increasing voltage is greater than the rate of increasing current, causing the ratio of V over I increases. The ratio of V over I equals R. This means that the resistance of filament lamp to increase. This is because at higher current and voltage to create the more heating effect and increasing the temperature of filament lamp, causing the resistance of filament to increase. IV characteristic graph of a diode. A diode is a component that allows current to flow in only one direction. This is the symbol for a diode, and it allows the current to flow in this direction. In this circuit, the diode allows the current to flow through the circuit, resulting in a reading on the ammeter. In this circuit, a cell is reversed, so the diode does not allow current to flow, resulting in no reading on the ammeter. The graph of current I in amperes against voltage V in volts of the diode is shown. In this side shows that the diode allow the current to flow through the circuit, resulting in high current, and the resistance of diode is very low. In this side shows that the diode does not allow the current to flow through the circuit, resulting in zero current, and the resistance of diode is very high. So, we can conclude that the semiconductor diode is another example of a non-ohmic conductor. A diode is any component that allows electric current in only one direction. This strangely shaped graph shows that diodes have a high resistance when the current is in one direction, and a low resistance when it is in the opposite direction. This shows that the diode only allows the current to flow in one way. A thermistor is a semiconductor used to detect temperature. As the temperature increases, the thermistor's resistance decreases, and vice versa. This property is called a negative temperature coefficient, NTC. This is a real thermistor. This is a symbol of the thermistor. The graph shows the thermistor's resistance plotted against temperature. A graph showing a thermistor's decreasing resistance with increasing temperature. A light-dependent resistor, LDR, is also a semiconductor used to detect light intensity. As the light intensity increases, the LDR's resistance decreases, and vice versa. This is a real LDR. This is a symbol of LDR. The graph shows the LDR's resistance plotted against light intensity. A graph showing an LDR's decreasing resistance with increasing light intensity. Exam style question 1. 4 wires are made of the same metal. The cross-sectional areas, lengths and thermodynamic temperatures of the wires are shown. Which wire has the largest resistance? The resistance, R, is inversely proportional to its cross-section area A. The resistance, R, is directly proportional to its length L. The resistance R increases as temperature increases. We give the resistance of the wire is R, given a cross-sectional area A, a length L, and a temperature T. Choice A. The cross-section area remains the same, so the resistance remains the same, becoming R. The length increases 2 times, so the resistance increases 2 times, becoming 2R. The temperature increases 2 times, so the resistance increases more than 2R. Choice B. The cross-section area remains the same, so the resistance remains the same, becoming R. The length remains the same, so the resistance also remains the same, becoming R. The temperature remains the same, so the resistance stays the same as R. Choice C. The cross-section area increases 2 times, so the resistance decreases 2 times, becoming half of R. The length increases 2 times, so the resistance decreases 2 times, becoming 2 times half of R equals R. The temperature increases 2 times, so the resistance increases more than R. Choice D. The cross-section area increases 2 times, so the resistance decreases 2 times, becoming half of R. The length remains the same, so the resistance stays the same as half of R. The temperature remains the same, so the resistance stays the same as half of R. So, the largest resistance is A. Exam style question 2. The wire of a heating element has resistance R. The wire breaks and is replaced by a different wire. Data for the original wire and for the replacement wire are shown in the table. What is the resistance of the replacement wire? The resistance, R, of the original wire equals ρ L divided by A. Substituting the cross-section area, A equals pi d squared dividing by 4, and simplifying as 4 ρ L over pi d squared. So, the resistance, R, is directly proportional to ρ times L and inversely proportional to d squared. The length of the replacement wire remains the same, so it has no effect to its resistance. The diameter d increases 2 times, so d squared increases 4 times, causing the resistance of replacement wire also decreases 4 times, resulting in 1/4 R. The resistivity ρ increases 2 times, causing the resistance of replacement wire increases 2 times, resulting in 1/2 R. So, B is correct. Exam style question 3. A resistor and a filament lamp are connected in series with a power supply. The IV characteristics of the resistor and of the lamp are shown below. The potential difference, PD, across the resistor is 3.3 volts. What is the resistance of the lamp? The resistor and lamp are connected in series, so the same current passes through them. In the IV graph of a resistor, when the PD across it is 3.3 volts, and the current passes through it is 0.3 amperes. In the IV graph of a filament lamp, when the current passes it is 0.3 amperes, and the PD across it is 4.2 volts. Using the equation V equals R times I, to calculate the resistance of a filament lamp. Substituting V equals 4.2 volts, and I equals 0.3 amperes. We get the resistance of lamp equals 14 ohms. Exam style question 4. A fixed resistor and a diode are connected in series to a battery of electromotive force, EMF, 6.0 volts, and negligible internal resistance. The graph shows the variation with potential difference, PD, V of the current I for the diode. The current in the diode is 40 mA. What is the resistance of the fixed resistor? The resistor and the diode are connected in series, so same current passes through them. In the IV graph of the diode, when the current in the diode is 40 mA, so the PD across the diode is 1.2 volts. As the PD across the diode is 1.2 volts, causing the PD across the resistor is 6 minus 1.2, resulting in 4.8 volts. Using the equation V equals R times I, to calculate the resistance of the resistor. Substituting V equals 4.8 volts, I 40 times 10 power negative 3 amperes. We get the resistance of the resistor equals 120 ohms. I hope you found this video helpful. If you did, I would be grateful if you would subscribe, share, like and leave a positive comment. Your support will encourage me to create more content. Thank you.